There are moments in the history of science that feel like whispers from the universe. Soft, delicate, yet powerful enough to shake everything we thought we knew. And today, standing before humanity's newest revelation, we find ourselves at that very threshold. For billions of years, the Big Bang has been treated as the sole opening chapter of existence. But as the oldest light ever recorded returns through the eyes of James Webb, it arrives like an ancient witness, telling a different tale. A tale longer, deeper, and filled with secrets never spoken aloud. What if what happened before the Big Bang was not nothingness, but a hidden chapter waiting to be found? What if time is not a straight line, but a river that remembers its own beginning? Share your thoughts in the comments below. What do you believe unfolded before the universe was born? And to understand why this mystery could shake the foundations of cosmology itself, we must begin with a question we thought was familiar. Is the universe truly 13.8 billion years old? Is less than number 1. Hash is greater than. The universe has always guarded its age, like a secret tucked beneath layers of starlight. And for more than a century, humanity bowed before a single number whispered through telescopes and equations. 13.8 billion years. Yet, in the quiet dark where galaxies drift like ancient lanterns, something has begun to stir. Something that suggests the number may not be a truth carved in cosmic stone, but a fragile estimate trembling under the weight of new evidence. Astronomer Wendy Friedman once said, "The universe is under no obligation to make sense to us." And perhaps, with the rise of the James Webb Space Telescope, we are witnessing the universe gently reminding us of that truth. Because Webb, like a golden eye floating a million miles from Earth, has opened a window into epochs so distant they touch the hem of creation. Through that window, we see galaxies that should not exist, stars older than our timeline permits, structures polished and mature when they should have been wild and newborn. And so the question rises naturally, like a tide meeting the moon. Why might 13.8 billion years be wrong? Perhaps because the first assumption we ever made about time came from a universe too young in our eyes, a universe we barely understood. Perhaps because light itself behaves in ways our oldest models never fully captured, or because cosmic expansion may carry subtleties as delicate as silk threads weaving reality together. As Webb gazes deeper, the early universe begins to look like a vast library whose books are bound long before the ink should have dried. Galaxies appear with tens of billions of stars, existing a mere 500 to 700 million years after the Big Bang. It is as though time had stretched itself generously, offering these galaxies room to grow before the universe had even learned to speak in starlight. Professor Garth Illingworth described his shock simply. "This is not what we expected." And it is not. Because according to every model we trusted, the first galaxies should have been tiny, clumpy, fragile collections of infant stars waiting patiently for gravity to sculpt them. Yet Webb shows us giants, compressed like cosmic diamonds, dense and luminous. Their mass, by all logic, belongs to galaxies birthed billions of years later. And there lies the impossible early galaxy problem. a phrase that sounds almost poetic in its contradiction, but carries the weight of a scientific crisis. How could so much matter gather so quickly? How could stars ignite in such abundance? How could structure rise with the maturity of civilizations long before there was time for them to grow? Some astronomers suggest supermassive black holes at their centers are tricking us, their bright disks imitating starlight. Some argue the early universe was denser, allowing star formation to accelerate like a flame finding oxygen. But even those ideas stretch the limits, bending physics like warm metal. Because the galaxy's web reveals do not look rushed or chaotic. They look ancient, wise, settled into form too early to be believed. As Nobel laureate Adam Rees once remarked, "When the universe tells you something you don't want to hear, listen harder." So we listen, and the whispers point toward a possibility many fear to say aloud. That perhaps the universe is older than we thought. 2 times older. Maybe more. That perhaps our calculations of redshift, cosmic expansion, and time itself carry assumptions too rigid for a cosmos that delights in bending expectations. For when we ask why these galaxies appear impossibly mature, we are really asking a deeper question. Does our timeline make sense? And if the timeline falters, then the age at its foundation must tremble too. Let us drift deeper, slowly, like dust moving through a beam of starlight, because the story does not end with galaxies that grow too quickly. There are stars within our own Milky Way whose ages brush dangerously close to 14 billion years. Stars like Methuselah, whose metallicity is so low it sings of an origin near the dawn of everything. These stars are like fossils floating through the dark, carved from an epoch almost primordial. They do not fit comfortably inside a 13.8 billion year timeline, no matter how we twist the equations or widen the error bars. Then there are the globular clusters, densely packed spheres of stars that formed so early. They nearly overlap with the universe's supposed beginning. Their existence leaves very little room for the first stars to die, scatter metals, cool the gas, and allow new generations to form. Time feels short, rushed, unnatural. It is as though the universe had sprinted in its childhood, only to slow to a crawl billions of years later. And yet, nature rarely sprints. She unfolds, slowly, rhythmically, with the patience of tides and mountains. So perhaps the problem is not the universe, but our clock. Astrophysicist Avi Loeb observed, "When data conflict with theory, it's the theory that must change, not the data." Maybe time before the Big Bang was not a void, not a blank page, but a chapter erased accidentally by our assumptions. Maybe the Big Bang was not the beginning, but the blooming of a seed planted in an older cosmic soil. And what existed before that seed bloomed? A cold universe expanding gently. A field of potential waiting for a spark. A previous cycle collapsing into this one. Or something far stranger than imagination allows. Professor Sean Carroll once mused, "The universe may not have had a beginning at all, just a phase before things changed." Let that idea rest softly in the mind, like a feather landing on water. Because if something existed before the Big Bang, then the timeline we measure from its fire is merely a continuation, not a creation. And the universe, in its true age, may stretch far beyond our oldest numbers. When I consider this possibility, I feel a peculiar peace, as though knowing the universe is older, wiser, more ancient than we imagined, somehow makes our existence feel more connected to something vast and enduring. A cosmic lineage that spans epochs before light learned to shine. The lesson it teaches feels gentle and humble. That certainty is a fragile lantern in a storm of stars. That curiosity must always outweigh comfort. That every answer opens a deeper question. And as James Webb continues to send back its silent revelations, the narrative grows richer, more layered. Galaxies that defy the clock, stars that whisper of forgotten ages, structures that shine brighter than youth should allow. Together, they form a cosmic chorus singing a single possibility. That time is older than we thought. And if time is older, if the universe is not 13.8 billion years but 20, 25, maybe more, then every mystery that once felt impossible begins to soften, make sense, unfold with elegance. The galaxies are no longer too young to be so large. The stars are no longer too ancient to exist. The clusters are no longer pressed uncomfortably against the universe's opening moments. Everything finds room to breathe, to grow, to become. And perhaps that is the most human part of this revelation. That understanding the cosmos is not about proving ourselves right, but about learning to listen when the universe whispers something new. In that listening, we find humility, wonder, and a renewed sense of awe for the ancient darkness that cradles us. And so, as we drift toward the next chapter of this story, with our minds open like night skies, we must ask gently, is time older than we dared to imagine? And what else awaits us in the deep silence before the first dawn of creation? The deeper we drift into the universe, the more its oldest lights begin to whisper truths we were never prepared to hear. Astronomers once believed the timeline of the cosmos flowed with calm certainty, beginning at 13.8 billion years, rising gently into the age of galaxies and stars. But when James Webb opened its golden eye and peered into the faint ember of the cosmic dawn, it saw not the fragile newborns we expected, but giants, ancient in shape, mature in mass, and impossibly evolved for their supposed age. As Nobel laureate John Mather said, "The universe is not obligated to make sense to us at first glance." These galaxies formed too fast, too bright, too organized, as though time itself had stretched or folded to allow them a head start over everything else. They spiral with calm geometry where there should only be chaos. They hold bulges with densely packed stars where there should only be the trembling glow of cosmic infancy. And they shine with the confidence of systems billions of years old. Nothing in our textbooks prepared us for this. Classical models of star formation tell us that gas cools slowly, collapses slowly, ignites slowly. Gravity may be patient, But star birth is always deliberate, and galaxies take their time, merging, colliding, negotiating their shapes over billions of years. Yet Webb saw mature disks only 500 million years after the supposed beginning. Webb saw spiral arms where cosmic turbulence should still reign. Webb saw bulges so dense they seemed like memories carried from a previous universe rather than creations of this one. As astrophysicist Priyamvada Natarajan once said, "Every time we think we've reached the limit of the possible, the universe hands us an impossible." Some scientists wondered whether the light deceived us, whether the monstrous masses of these galaxies were illusions painted by supermassive black holes at their centers, their glowing accretion disks masquerading as stars. Others suggested that in the early universe, gas clouds were thicker, denser, more tightly wound by gravity, making stars ignite faster. But even these ideas strain against the sheer scale of the numbers, for the galaxies we observe are not just large, they are enormous, not just mature, but eerily evolved. And so the whisper grows louder. Perhaps the timeline is wrong. Not by a little, but by an ocean of time. Perhaps 13.8 billion years is not the age of the universe, but merely the age of the chapter we can see. The great astronomer Alan Sandage once wrote, "The universe is a story still being edited." And maybe Webb has shown us that half the pages are missing. If galaxies look older than the universe, then it is not the galaxies that are out of place. It is our clock that is broken. A clock wound tightly by assumptions that no longer hold. A clock built from light we misinterpreted because we were convinced the expansion of space was the only author of redshift. But what if the light has grown tired as it travels, losing energy to the quiet fabric of space itself? What if the constants that guide the dance of particles were once different, shaping cosmic history according to rules we have not yet learned? Rajendra Gupta warned the community. Nature has a way of hiding the truth in places we stop looking. And maybe this is one of those places. When I look at these early galaxies, I sense not contradictions, but nostalgia. As if the universe remembers something older than 13.8 billion years, something deeper. A long-forgotten overture played before the Big Bang struck its famous first note. Their shapes feel too calm for cosmic infancy, their spirals too deliberate, their cores too wise, like ancient travelers who arrived here already carrying the weight of distant aeons. If this is true, the lesson becomes profoundly human. Our knowledge, no matter how precise, is always temporary. Our models, no matter how elegant, are always drafts, and the universe, patient and silent, is always more ancient than our bravest imaginations. Perhaps the real question is not, how did galaxies grow this fast? But why did we believe they couldn't? Perhaps history is not linear, but cyclical, not a line, but a spiral, like the galaxies themselves. As Neil deGrasse Tyson often reminds us, the universe is under no obligation to make sense on our schedule. And maybe that is the quiet mercy of this discovery. It invites us to slow down, to breathe, to accept that our cosmic story is deeper, longer, more intricate than we dared believe. If you are listening to this in the soft stillness of night, let these possibilities drift with you. them remind you that we are made of the same elements that burn in those impossible ancient galaxies. And if the universe is older than we thought, then so too is the story written into our atoms. As for me, I believe these discoveries teach us humility. They teach us that certainty is the rarest element in the cosmos, and that curiosity is the force that binds us together. Every new galaxy Webb reveals feels like a reminder that the cosmos favors those who continue to ask, even when the answers become uncomfortable. If this journey has sparked something in you, a question, a wonder, or simply a feeling of drifting among the stars, let me know in the comments. Share your thoughts, your theories, your dreams of what an older universe might mean. Your voice becomes part of this cosmic conversation. And if you wish to travel further with me through these vast mysteries, like this video, subscribe to the channel, and let us drift together through the deep quiet of the universe. For now, let us leave one last question hanging gently in the dark. If these galaxies are older in spirit than our timeline allows, then perhaps we are asking the wrong question. Perhaps the universe is not young, but we are, and the true age of everything waits patiently just beyond the next horizon of light. The story of our universe has always felt like a quiet chant drifting through cosmic darkness, an ancient rhythm that guides us from the first spark of creation to the edge of our own understanding. For over a century, humanity has repeated the same number in textbooks and observatories and midnight conversations under the stars. 13.8 billion years. A number spoken with the confidence of a timeline engraved in stone. A number that once felt like the heartbeat of the cosmos itself. And yet, as we listen more closely to the music of the universe, that certainty begins to tremble like a thin note held a little too long. The belief in a 13.8 billion year universe began with a man who pointed a telescope toward a sky that seemed quiet. Edwin Hubble, standing at the threshold between the known and the unimaginable, noticed something no one had truly seen before. Light stretching, wavelengths pulled like threads, unraveling on a loom of space itself. Galaxies drifting away as though carried by a tide older than memory. He called it redshift, and from that moment the universe was no longer still. Hubble once said that the history of astronomy is a history of receding horizons. And with those horizons came the idea that the farther a galaxy moved, the faster it seemed to flee from us. The slope of that relationship, the Hubble constant, became the ruler with which we measured the age of everything. If the universe had been expanding since the beginning, then rewinding that expansion like a cosmic film reel should lead us back to the first frame. And so scientists took the speed of expansion, flipped it backwards, and declared the moment of origin to be roughly 13.8 billion years ago. But the universe does not yield itself so easily. It resists with a kind of gentle defiance. Stephen Hawking once reminded us that the universe has not only a history but a sense of irony. And nowhere is that irony clearer than in the constant that bears Hubble's name. Because this number, this supposedly universal rate of expansion, has refused to stay still. It has wandered for decades, shifting with each new measurement, drifting like a star caught between gravitational tides. In the early 20th century, it suggested a universe barely 2 billion years old, younger than Earth itself. an impossibility whispered into silence. Then it stretched to 20 billion, then fell again, swinging like a pendulum, unsure of its true rhythm. Even today, with instruments of extraordinary precision, the Hubble constant refuses agreement. Local measurements give one value. The cosmic microwave background gives another. Between them lies a gulf so persistent that Nobel laureate Adam Rees calls it the most important problem in cosmology. And so the timeline trembles. Shaken not by speculation but by evidence so clear it glows like embers in the dark. When James Webb opened its golden eyes, astronomers expected to see the faint blue sparks of newborn galaxies. Instead, they found giants, ancient in appearance, massive beyond reason. These galaxies stood where only fragile cosmic infants should exist, defying the rules we thought governed the early universe. One scientist simply whispered, "It's bananas." And perhaps that was the most honest response of all. Because these galaxies were not anomalies. They were revelations. They carried the weight of billions of stars at a time when the cosmos should barely have been capable of lighting its first candles. They showed organization, structure, maturity, qualities that demand time, far more time than our cherished timeline allows. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And this feels like the whisper of that incredible thing. A quiet suggestion that the story of our universe is longer, older, more patient than we imagined. But to accept that possibility, we must return to the beginning of our belief, to the moment Hubble saw the galaxies drifting and interpreted the drift as a uniform expansion. A beautiful idea, elegant in its simplicity. But the universe rarely aligns with our desire for elegance. The Hubble constant is not constant. It is a river whose flow changes depending on where we stand, what we measure, and how we look. What we once saw as a fixed value may actually be a shifting signature of cosmic history, a melody whose tempo changes from one era to another. Physicist Subramanian Chandrasekhar once remarked, "Science is a perception of the world around us," hinting that perceptions can deepen as instruments sharpen. And sharpen they have. The discovery that different methods produce different values of the Hubble constant is not a minor disagreement. It is a wound through the heart of cosmic chronology. If the universe expands faster now than it did in the past, or if light behaves differently over great distances, then the equation tying redshift to time may be flawed in its simplicity. And flaws in that equation ripple through everything, stretching or compressing the timeline like a fabric that has been pulled too tightly on one side and left loose on the other. Modern astronomers speak softly about this tension, not out of fear, but reverence, because they sense that beneath it lies a fundamental truth. The universe is not on our schedule. It does not age according to our preferences. It does not comply with the neat boxes in our textbooks. Each new measurement feels like a breath drawn in meditation, a moment of stillness that reveals how much the cosmos has been trying to tell us. Perhaps the universe is older than 13.8 billion years. Perhaps much older. Or perhaps age itself is not the linear staircase we imagined, but a spiral, curving gracefully through epochs we have not yet learned to see. redshift, once our most trusted cosmic compass, may carry more than the imprint of expansion. It may also hold the subtle fatigue of photons traveling through ancient distances, or the changing whisper of fundamental constants evolving with time. The beliefs we formed a century ago were reasonable, built on the best light we had. But as new light arrives, we must let our certainty soften like dust drifting in a sunbeam. The universe has never asked us to be right, only to be willing to see. And so we stand at the edge of a question that glows like a lantern in the dark, inviting us deeper into the unknown. If our cosmic timeline is breaking, if the universe is older than we believed, then everything from the birth of the first stars to the dance of galaxies must be seen with new eyes. Nothing has changed in the universe, only in our understanding. And with each revelation, we float a little further into the vastness, listening to the stars as though they were singing a story long before we learned how to hear it. Perhaps that is why the question persists like a quiet heartbeat beneath every measurement and every doubt. Is the universe truly 13.8 billion years old? In the quiet vastness of the cosmos, where light drifts like ancient pollen through an endless night, the story of time itself moves slowly, like a river remembering the shape of its earliest stones. Astronomers once believed this river was well charted, flowing for exactly 13.8 billion years, according to the soft glow of the cosmic microwave background. Yet as new measurements arrived from distant supernova, the river suddenly seemed shorter, narrower, as though it curved in ways we never noticed before. These two clocks of the universe, the brilliant explosions of Type Ia supernova and the primordial whisper of the CMB, began to disagree. One suggested an age of only 12.5 to 13 billion years, while the other held firmly to 13.8. Like two storytellers who witnessed the same sunrise but stood in different valleys, they spoke of similar light yet measured different dawns. This disagreement is what cosmologists call the Hubble tension, a phrase that sounds technical but beneath it lives a poetic wound in the fabric of our understanding. Adam Rees, Nobel laureate, once said, "When precise measurements disagree, nature is trying to tell us something." And indeed, the universe seems to be humming a melody that does not fit the instruments we built to capture it. The supernova measure how quickly space is expanding around us today, while the CMB measures how fast it expanded long ago. And these tempos do not match. It is as if the cosmos breathes in two rhythms at once, one old, one new. Some say this is simply a measurement error, a smudge on the lens, a calibration drifting like dust across mirrors of billion-dollar telescopes. Others whisper that perhaps the model we use to describe the universe, the cherished lambda CDM model that has guided cosmology for decades, may be missing a verse in its cosmic poem. Priyamvada Natarajan of Yale once remarked, "When the universe surprises us, it is rarely the universe that is wrong. Perhaps the error is not in the stars, but in our assumptions of how they came to be." This tension grows deeper when we look not at supernova, but at ancient stars in our own cosmic backyard. Among them drifts one that defies explanation, a lonely wanderer in the constellation Libra known as Methuselah star, HD 140283. When astronomers first measured its age, the number fell like a stone through their equations. 14 billion years. Then, 14.5. Some estimates even brushed against 16 billion years, a number older than the universe itself, if we trust the Standard Model. How can a star be older than everything that contains it? Older than space? Older than time? The paradox is quiet but devastating. Like seeing a child who somehow remembers the birth of their great-grandparents. An impossible memory that forces us to rethink the lineage of cosmic history. Methuselah's low metallicity, its elementally pristine nature, says it was born when the universe was still young. Yet the models of stellar evolution, the very scripts we use to estimate ages, seem to place its birth before the curtains of time even opened. Some scientists argue that the models are flawed, that internal mixing, opacities, or unknown nuclear processes make the star appear older than it is. But others point gently toward a different possibility, one both wondrous and unsettling. The age of the universe itself may be wrong. As cosmologist Avi Loeb said, "The universe is under no obligation to make sense to us." When James Webb revealed giant galaxies forming impossibly early, it was as though the universe whispered again, urging us to listen more closely. Because if galaxies were already ancient and massive when the universe was supposedly only 500 million years old, then the cosmic clock may indeed be ticking differently than we believe. And if these galaxies are older or larger than the timeline allows, then stars like Methuselah no longer stand alone in their defiance. Imagine the timeline of the cosmos as a tapestry, and these anomalies as threads pulling loose at the edges. The tension in the Hubble constant pulls from one side, the ancient stars pull from another, and in the center, the fabric bends. Not breaking, but reshaping. Perhaps the universe is older than 13.8 billion years. Maybe 14. Maybe more. Perhaps time in the early cosmos stretched differently. Or photons lost energy in subtle ways as they crossed expanding space. Perhaps gravity or dark energy evolved, shifting the tempo of the cosmic expansion. Or perhaps something deeper awaits us, something as yet unnamed, curling beneath equations like a tide we cannot see. In moments like this, I think of Carl Sagan, who once said, "Somewhere, something incredible is waiting to be known." And indeed, these cracks in our cosmic timeline may be the points where the incredible begins to rise. For when two clocks disagree, it is not simply confusion. It is an invitation, an opening toward discovery, a reminder that the universe is not merely facts and equations, but a living poem still being written in starlight. As we drift through these questions, one truth remains clear. Our understanding is not complete. The universe does not owe us consistency. And yet through these contradictions, it gently guides us toward deeper truth. Perhaps Methuselah is not older than the universe, but our vision of the universe is younger than reality itself. Perhaps cosmic time is not a rigid line, but a flexible fabric, softly stretching across epochs we are only beginning to sense. And as we follow this thread, drifting like travelers across a dark ocean, we may come to see that the timeline of the cosmos was never broken. It was only misunderstood. For now, all we have are clues, starlight, and questions unfolding like petals toward a dawn we have yet to witness. But as long as we continue to listen to the universe's quiet corrections, we may one day understand why one clock tells us 13 billion years, while another whispers 13.8, and why a lone star dares to claim an age that echoes before the beginning itself. Until then, we drift in wonder, humbled by mysteries older than time, and soothed by a cosmos that continues to teach us how young our knowledge truly is. The night sky has always felt like a soft reminder that time is not a straight line. It is a tide that rises, falls, and sometimes loops back on itself in ways we barely understand. When we lift our eyes toward the ancient clusters of stars that hang like glowing seeds across the cosmic dark, we are not simply looking at light. We are looking at memory. Memory older than our models, older than our textbooks, older than the fragile certainty we have built around the number 13.8 billion years. And as we drift through this story together, slowly and calmly, like travelers floating down a river of stardust, we begin to sense that something in the cosmic timeline has come loose. Astronomers have long believed that the universe has an age fixed by the afterglow of the Big Bang, the cosmic microwave background. But when they gazed into the halos of our Milky Way, they found ancient globular clusters whose stars whisper a different tale. These clusters are not newborns of the cosmos. They are elders. Ancient congregations of stars packed so tightly that they feel almost like the beating heart of time itself. Many of them are measured to be around 13 to 14 billion years old. So old that they brush dangerously close to the very age we assign to the universe. It is as if a child claimed to have lived as long as their parent, and somehow the math refused to forbid it. The question arises softly, like a breath in the dark. How could these clusters form so soon after the Big Bang, in an era when the universe was still cooling from its first fire? The time between the cosmic dawn and the earliest formation of these clusters appears almost too thin, too hurried, too compressed to be believable. Even the most generous models struggle to explain how stars could gather in such dense, orderly structures so soon after the universe opened its eyes. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And perhaps that something lies hidden in these clusters, quietly challenging the story we tell about cosmic origins. In recent years, astronomers developed new techniques to age these clusters, looking not only at their oldest stars but at the curious blue stragglers that hide among them. These blue stragglers shine brighter and hotter than their neighbors, as if they have stolen youth itself. By studying them, scientists found hints that the clusters may be older than previously measured, suggesting that the cosmic clock may tick more slowly than our equations assume. Some calculations even hint that the universe must be older to comfortably contain these celestial elders. And then comes Rajendra Gupta, with a theory as delicate and radical as a whisper cutting through the silence of space. He does not ask us to throw away the Big Bang, nor to deny cosmic expansion, but to reconsider what redshift truly means. For decades, we treated redshift as a measure of distance stretched by cosmic expansion. The farther the galaxy, the more its light is pulled into the red. But Gupta weaves a more subtle picture, suggesting that some of this shift may come not only from expansion, but from a gentle tiredness of light itself. The tired light concept was introduced nearly a century ago, then discarded because it could not explain time dilation in supernovae. Yet Gupta does not revive it fully. He threads it carefully into expansion models, allowing it to play a small, partial role. If a fraction of redshift comes from this quiet loss of photon energy over vast stretches of time, then galaxies we believe to be extremely distant and extremely young might actually be closer, older, more mature than assumed. This alone stretches the cosmic timeline, opening new space for ancient stars, ancient clusters, ancient histories that our previous calendar could not contain. But Gupta goes further, touching one of the most sacred assumptions in physics: the constancy of physical laws. He proposes that coupling constants, the strengths with which particles interact, might have evolved across cosmic time. This is not without precedent. The physicist Paul Dirac once mused that the gravitational constant itself may have drifted as the universe aged. If constants shift, even slightly, then the universe could be older than we imagine and yet still produce the cosmic microwave background we observe today. Stephen Hawking once reminded us, "The greatest enemy of knowledge is not ignorance. It is the illusion of knowledge." Perhaps the illusion is that our cosmic clock is perfect. If Gupta is right, even partially, the universe may not be 13.8 billion years old, but 26.7 billion. Nearly twice the age we believed. Enough time for globular clusters to gather themselves gently, for ancient stars to burn slowly, for cosmic rhythms to unfold at a pace more fitting the grandeur of existence. And yet, cosmologists remain cautious. Because if redshift is not purely expansion, what else whispers beneath it? Could evolving constants have subtly shaped the universe's story, altering the behavior of matter and light in ways we have not yet mapped? As we drift deeper into these questions, it becomes clear that science is not a rigid monument, but a living conversation with the cosmos. The ancient clusters look back at us with quiet patience, as if saying that time is wider than our equations and older than our confidence. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you." And yet we try. We try because the stars call to the human spirit, inviting us to ask again and again whether the story we tell is truly the story written in light. We try because the oldest globular clusters glow like lanterns on a forgotten shore, hinting that the coastline of cosmic history stretches farther than we dared to walk. And so, as the universe continues to expand or perhaps expand and evolve and whisper away the energy of photons, we remain here, listening, quietly, patiently, tracing the faint threads of light that slip through billions of years to reach our small world. Perhaps the timeline was never broken, only incomplete. Perhaps the cosmos has simply waited for us to look long enough, gently enough, deeply enough to see that its age is not a number carved in stone, but a river still flowing. And as we float through this cosmic meditation together, we realize something serene, something beautiful. The mystery of the universe's age is not a problem to be solved, but an invitation to wonder. An invitation to listen to the elders of the sky, to question the constancy of the laws we hold dear, and to follow the faint red glow of distant galaxies until we understand whether expansion alone writes the story of their light. In the end, the universe may be older than we think, younger than we assume, or stranger than anything we have yet dared to imagine. But as long as there are stars to gaze upon, and minds willing to drift among them, the search for truth will continue. A journey not of certainty, but of awe. In the quiet velvet of the universe, where ancient light glides across distances too large for human imagination to grasp, there lies a number that has shaped our understanding of time itself. Redshift, the cosmic stretching of light, the gentle pulling of wavelengths as space expands, has long been treated as a faithful storyteller of the past. It whispers how far a galaxy is, how old its light has traveled, how early, in cosmic history, it bloomed. Yet today, in the soft hum of new observations and the trembling edge of new physics, that whisper feels uncertain. As if the universe, with a poetic smile only it could wear, is hinting that the story we thought we understood was only the prologue. For a century we trusted that when light stretches its glow into deeper reds, it is because space between us and the emitter has grown, a cosmic breath expanding since the dawn of time. Edwin Hubble's discovery became the compass by which we navigated the ages, turning redshift into a ruler that measured not only distance but the very tempo of creation itself. "The universe is expanding," he wrote, and the world listened. But as modern telescopes peer farther than Hubble ever dreamed, the familiar map begins to ripple, as though the ink of cosmic history has not yet dried. James Webb Space Telescope, with its gold mirrors and patient infrared eyes, has found galaxies so massive, so mature, so perplexingly old at high redshift, that astrophysicist Emma Chapman said, "They should not exist this early in time." These galaxies shine like ancient giants dressed as newborns, proudly breaking every rule we wrote for them. According to the standard interpretation of redshift, some of these galaxies lived only 300 to 500 million years after the Big Bang, and yet they carry the mass and structure of systems that should require billions of years to form. So the question rises like a dawn behind dark mountains. Slow, luminous, inevitable. What if our conversion from redshift to time is flawed? What if these galaxies are not impossibly old, but simply not as early as we think? Here, a controversial idea returns from the wilderness of forgotten theories. Tired light. A notion first offered by Fritz Zwicky, who said, "Light may lose energy over great distances." In his view, photons could bleed energy to the cosmic medium as they travel, stretching into red without requiring space to expand as dramatically as we assume. The idea was dismissed because it failed to explain several key phenomena, especially the time dilation seen in distant supernovae. But today, some physicists whisper that perhaps tired light is not the whole story, but part of a hybrid one. If even a small fraction of observed redshift comes not from expansion but from energy loss, then our calculations of distance become longer than reality, and our estimates of age become shorter than truth. In that possibility, the so-called early galaxies are not early at all, merely misdated by a ruler that bent slightly under our assumptions. As physicist Rajendra Gupta remarked, "If your clock runs too fast, you will think the universe lived less time than it truly has." Imagine the cosmos like a river, its currents twisting through depths unseen, carrying fragments of starlight as if they were petals drifting from ancient trees. If the river slows, if its waters drag against hidden stones, the petals may arrive late, yet appear to have traveled farther. Perhaps redshift is like that, a beautiful signal with more than one cause. And if so, our cosmic timeline may have been compressed without us noticing. This does not break physics, but folds it gently, like fabric being gathered by an unseen hand. After all, the universe has surprised us before. Einstein's cosmological constant, once abandoned, returned as dark energy. Quantum entanglement, once ridiculed, is now a pillar of modern computation. Why should redshift be immune to such reconsideration? Yet if tired light plays even a small role, astronomers must ask the next unsettling question. Have we mistaken the age of the universe? If galaxies at redshift 10 are not 500 million years after the Big Bang, but perhaps 1 or even 2 billion years later, then cosmic dawn becomes a gentle sunrise rather than an instant flash. The early universe becomes older, more patient, more like an artist layering starlight over eons rather than rushing to complete the first sketch. Cosmologist Wendy Friedman once said, "When two measurements of the universe disagree, the universe is telling us we have missed something." Indeed, the Hubble tension itself, the disagreement between supernova measurements and cosmic microwave background predictions, hints that our interpretation of redshift may not be absolute. Supernova Ia suggest a universe around 12.5 to 13 billion years old, while the CMB implies 13.8 billion years. Two clocks ticking in the same cosmos, yet telling different times. If redshift has multiple contributing factors, these clocks may not be wrong, merely calibrated against different layers of cosmic reality. In this meditative space, where science drifts into poetry, the universe feels less like a mechanism and more like a memory of light, stretched and softened by journeys too grand for numbers alone. Perhaps the galaxies we call primordial are not rushing into existence hours after the cosmic dawn, but are ancient cities whose outlines were blurred by misunderstood distance. Their red glow is not the fire of youth, but the ember of age. Even the stars themselves seem to whisper similar doubts. Consider Methuselah, the star whose estimated age once reached 16 billion years, older than the universe that cradles it. Stellar physicist Howard Bond said, "Either the star is younger than it appears, or the universe is older than we think." Redshift lies at the heart of that question. If our cosmic distances are stretched by assumptions rather than reality, Methuselah's age ceases to be paradoxical. The universe, in this view, becomes a place where time is not a straight road but a garden with winding paths. A place where light grows weary, where expansion sings with hidden harmonies, where equations hold secrets they reveal only when we dare to ask different questions. None of this diminishes the beauty of the cosmos. Instead, it deepens it. Every mystery is a doorway, every contradiction a lantern, lighting a new part of the night. And as we walk into that night, guided by starlight older than continents, we find ourselves humbled by how much remains undiscovered. So we meditate on redshift not as a failure, but as an invitation. The universe is under no obligation to make sense to you, Neil deGrasse Tyson once said. And yet, in its own quiet way, it does. It reveals itself gently, like a tide moving over shorelines of truth. Perhaps the earliest galaxies are not infants, but elders, standing at the frontier of our misunderstanding. Perhaps light does more than travel. Perhaps it suffers, transforms, remembers. And perhaps the cosmos, patient and ancient, has been waiting for us to notice. Until then, redshift remains both map and mystery, a gentle riddle written in the faintest ink of time. And as we drift through this great ocean of night, our questions become constellations, guiding us forward toward a truth that glimmers just beyond the horizon. The universe has a way of speaking to us in moments of sudden brilliance, moments when the night sky erupts with a light so ancient, yet so immediate, that it feels as though time itself holds its breath. Among the most powerful of these cosmic messengers is the supernova, a stellar ending that becomes a beginning for our understanding of reality. When a star dies, its explosion ripples through space-time like a slow tidal wave of memory, carrying with it secrets that science has chased for generations. And in those luminous echoes resides one truth that refuses to be bent or softened. A truth that quietly dismantles one of the oldest alternative explanations for the expansion of the cosmos, the tired light hypothesis. For nearly a century, tired light proposed that the redshift of distant galaxies was not the stretching of space-time, but merely the fatigue of photons losing energy as they traveled across unimaginable distances. A gentle dimming, as if light itself aged like an old traveler wandering through the void. It was an idea that appealed to a universe that might remain static and eternal, a cosmos without a beginning or end. But then came the supernovae, brilliant, unforgiving, and precise in the language they speak. And with each explosion recorded by our telescopes, the universe whispered the same message over and over again. Time dilates, and tired light cannot explain it. When we observe a Type Ia supernova across billions of light-years, something extraordinary happens. The light curves stretch. The rise and fall of brightness grows longer, as though someone has gently pulled the film reel of the universe into slow motion. What should take days takes weeks. What should take weeks takes months. This stretching of time is not a trick of distance. It is not an illusion of tired photons. It is the inevitable consequence of space-time expanding of every second that once ticked near the supernova being stretched by the swelling of the cosmos itself. Adam Rees, Nobel Prize-winning astrophysicist, once said, "The universe is not just expanding. It is telling us about that expansion through the slowing heartbeat of distant supernovae." His words flow like a quiet confirmation of what the cosmos has been teaching us all along. If tired light were true, we would see dimming without stretching, reddening without slowing, distance without dilation. The universe would fade but not breathe, grow fainter but not grow older in our eyes. A tired photon loses energy, but it does not stretch time. It does not slow the rhythm of a stellar death. And so the light curves of supernovae become a quiet but decisive verdict, ruling out a universe where photons simply age on their way to us. As astronomer David Branch once noted, if tired light were the answer, supernovae would look dimmer but not slower. Yet the universe shows us both. In the meditative silence of the cosmos, this becomes a beautiful contradiction, a cosmic koan whispered through collapsing stars. Why does the universe allow light to fade but also allows time to stretch? Why does it ask us to look deeper than the simple fatigue of a photon? The answer flows gently through the mathematics of relativity, through the understanding that time and space are entwined like breath and heartbeat. When the universe expands, it stretches the wavelengths of light, and it stretches the heartbeat of events, slowing their rhythm. We are not just looking across distance, we are looking across time's own transformation. To honor this idea fully, imagine watching a candle burn in a distant valley, and as you watch, the flame seems to rise and fall in slow motion. Not because your eyes are dimming, not because the candle is weakened by fatigue, but because the valley itself is drifting away, stretching the very seconds that define the candle's flicker. That is the truth of supernovae. They do not just travel to us. They bring with them the dilation of time. If tired light were to survive as a theory, it would need to do something nearly impossible. It would need to mimic the precise, measurable, predictable stretching of time itself. It would need to grow weaker while also slowing the observed unfolding of cosmic events. It would need to invent a mechanism through which photons do not simply lose energy, but alter the flow of time in perfect alignment with relativity. No such mechanism exists. No modification of tired light has ever succeeded in reproducing supernova time dilation while preserving the clarity of other cosmological observations. In the words of cosmologist Brian Schmidt, time dilation is not optional. It is woven into the fabric of an expanding universe. And so supernovae become more than stellar explosions. They become teachers, cosmic monks performing a final meditation that radiates across the universe. Their light curves unfurl like long breaths, slow and stretched, telling us a story in the only language that cannot be forged or imitated. The language of time itself. A tired photon cannot stretch time, but an expanding cosmos must. There is something poetic in this, something almost tender in the way the universe reveals its truth through endings rather than beginnings. The death of stars becomes the birth of understanding. The collapse of a stellar core becomes a doorway through which we glimpse the architecture of reality. In this sense, supernovae are not merely explosions. They are cosmic storytellers, narrating the expansion of space-time with every stretched heartbeat of their fading light. As we drift through this reflection, one question echoes softly beneath all others. Why does the universe choose such violent beauty to communicate its deepest truths? Why does the end of a star carry knowledge that reshapes the fate of cosmological theories? Perhaps it is because destruction is clarity. Because in that moment when a star can no longer hold itself together, the universe offers us a glimpse of its own ongoing transformation. As Carl Sagan once whispered across decades, we are a way for the cosmos to know itself. And in the stretched light of supernovae, the cosmos is indeed knowing itself through us. The truth is gentle yet immovable. Supernovae show time dilation. Tired light does not. Supernovae slow down. Tired photons cannot. Supernovae whisper expansion. Tired light echoes only decay. And in this difference, the universe declares where reality truly lies. As we float now at the quiet edge of this meditation, we can almost feel the long, stretched breathing of the cosmos itself. It asks us not to cling to simple models of fatigue, but to embrace the profound truth that time and space are alive with motion. The universe expands, and in doing so, it stretches the stories written in light. It dilates the final heartbeat of stars, allowing us to read the history of everything in the slowing glow of their last moments. And so we return to the central question with a quieter heart. How do we know the universe is expanding? Because the dying breaths of distant stars arrive not only redder, but slower, longer, older. Because the universe has stretched their time just as it stretches their light. Because no fatigue of photons can imitate the poetry of space-time expanding. And because in every supernova we witness across the abyss, the cosmos is whispering its truth once more. Time is not fixed. Time is elastic. Time expands with the universe. That is why tired light fades, and supernovae endure. The cosmic microwave background drifts across the universe like an ancient breath, a soft relic of a moment when the cosmos was still young enough to glow like a newborn ember. When we listen to it through our instruments, it feels as though we are pressing our ears against the chest of creation itself, hearing the faint heartbeat that has echoed for nearly 14 billion years. Yet even this heartbeat, the most sacred evidence in the story of the universe, may not be the absolute truth we once believed it to be. Scientists have long treated the CMB as the gold standard of cosmology, a flawless fossil of the moment matter and light first parted ways. A time when the universe cooled enough for atoms to form and photons to roam free. But as we look deeper into the sky, guided by telescopes far more sensitive than our ancestors ever imagined, we begin to see gentle tremors in this perfect surface. The tiny fractures that whisper a simple but profound question. What if the CMB is not telling us the whole story? The idea seems almost heretical because the CMB feels like scripture etched in radiation. A map of early density fluctuations painted in blues and reds, so delicate that even a shift of 1 part in 100,000 holds meaning. But a few cosmologists have begun to wonder if this map could also fit a universe older than we think. Perhaps twice as old. Stretching back not 13.8 billion years, but something closer to 26. Rajendra Gupta once said, "If the universe's timeline seems too tight to explain what we see, then perhaps it is the timeline that must give way." His suggestion that the cosmos might be 26.7 billion years old startled many. Yet when laid beside the CMB, the idea does not fall apart as easily as expected. For while the CMB carries the memory of the early universe, it does not explicitly forbid an older one. It only encodes the physics of a moment long after the true beginning may have occurred. Imagine this background as a veil rather than a wall, a curtain drawn across the stage of the early cosmos. We see the universe as it was when it became transparent, but we cannot yet see what existed before. How long the darkness lasted. How long inflation may have stretched space before the CMB ever formed. The CMB is a photograph. Yes. But a photograph only captures the moment you press the shutter. And in that photograph we find anomalies. Tiny imperfections that have bothered scientists for decades. These are not loud contradictions, but soft disturbances. Ripples in what should be smooth. Asymmetries in what should be uniform. They are like small notes out of tune in a cosmic symphony otherwise perfectly played. The first is the famous cold spot. An unusually large and unusually cold region of the sky that should not exist in a perfectly random field. Yet there it is, staring back at us like a bruise on the skin of the cosmos. Some have suggested that it may be a statistical fluke, but others whisper that it could be a relic of something deeper. Perhaps a shadow cast by an enormous void, or even the imprint of another universe brushing against ours. The physicist Laura Mersini Houghton once remarked, "The cold spot may be the first data-driven hint that we are not alone on the cosmic stage." Then there are the large-scale anomalies. Patterns stretching across vast swaths of the sky that defy the expected randomness dictated by inflation. These include alignments that seem suspiciously coordinated, as if the early universe preferred certain directions over others. Physicists call this the axis of evil, with a mix of humor and unease, because it suggests a universe with memory, a universe with structure older than the CMB itself. And hovering above it all is the dipole asymmetry, a gentle lopsidedness in the CMB temperature that cannot be fully explained by our motion through space. It is as if the universe itself is pulling slightly in one direction, leaning toward an imbalance that no known mechanism should create. These anomalies do not scream, but they murmur, softly, persistently, like the faint cracking of ancient paint on a fresco that has endured too many centuries. And when the timeline of the universe is stretched to 26 billion years, some of these murmurs become easier to interpret. An older universe grants more time for pre-CMB processes to unfold, more time for inflation to leave deeper scars, more time for subtle gravitational imprints to shape the anisotropies we observe. Some cosmologists argue that the cold spot could be the remnant of a massive early void that had far longer to evolve. Others suggest the dipole might emerge naturally from extended pre-recombination conditions. And as for the large-scale alignments, an older timeline softens the contradiction between theory and observation, because it allows the early universe more freedom to develop structure before the CMB froze its image. Stephen Hawking once said, "The universe is under no obligation to make sense to us." Yet we keep asking, keep listening, keep tracing the faintest vibrations of the oldest light we can find. In this slow and meditative exploration, the CMB becomes less of a definitive proclamation and more of a gentle clue. A hint of deeper history hidden behind a glowing veil. The universe may be older than its own light suggests, just as a person's soul may be older than their face reveals. The longer we stare into the CMB, the more it resembles an ancient manuscript written in a language we only partially understand. Each pattern could be a sentence, each asymmetry a metaphor, each anomaly a forgotten page fluttering beneath our fingertips. And so we drift through these questions, slowly, like travelers floating in a quiet cosmic river, letting the starlight pool around us, letting science and wonder intertwine. Perhaps the universe is not younger or older, but simply vaster than our current imagination allows. Perhaps the CMB is not a boundary, but an invitation. And perhaps, as we listen to its ancient whisper, we will learn not only how old the cosmos is, but how young our questions have always been. In the quiet vastness between galaxies, where light drifts like ancient pollen and gravity hums its low eternal song, there lives a presence we cannot touch, yet cannot deny. Dark matter, silent and invisible, moves through the universe like a ghost whose footsteps shape the destiny of worlds. It does not shine. It does not whisper, and yet every star we have ever seen was born because of its gentle pull. As astrophysicist Vera Rubin once said, "We are reaching out to the invisible." And indeed, the invisible has guided us from the very beginning. When we ask how long dark matter needs to gather itself into the first halos capable of birthing galaxies, we are asking a question older than starlight. We are asking how long it takes for structure to rise from the quiet chaos of the newborn cosmos. In the standard timeline of 13.8 billion years, the fabric of the early universe was dense, hot, restless. Dark matter particles drifted freely through this primordial fog, clumping where gravity found footholds. Slowly, over tens and hundreds of millions of years, they formed halos, invisible wells that would cradle the first galaxies like cupped hands catching falling embers. Yet even with this poetic patience, the universe as we see it through the James Webb Space Telescope refuses to follow the script we wrote for it. At redshift 10, when the cosmos should be merely 450 to 500 million years old, we find galaxies with billions of stars, too large, too bright, too mature to fit inside the narrow frame of the timeline we believed in. As Professor Priyamvada Natarajan remarked, Webb is catching galaxies that simply should not exist yet. Their very presence bends the logic of cosmic evolution, just as dark matter bends the paths of light through empty space. To understand why these colossal structures defy the standard timeline, we must follow dark matter back into its earliest dances. In simulations based on the 13.8 billion year universe, dark matter halos grow slowly through mergers, a gentle accumulation like snow drifting into dunes across an ancient desert. Small halos meet, collide, settle, and gradually build the scaffolding that galaxies cling to. The process cannot be rushed because dark matter does not interact through electromagnetism. It does not radiate energy. It cannot shed heat quickly. It gathers only through gravity, the faintest of tugs, the softest of hands. This creates an inherent cosmic tempo, a rhythm written into the laws of nature themselves. Halos need time to grow, to merge, to reach the mass required to cradle the great star cities we call galaxies. In a universe only 500 million years old, the mathematics insists the largest structures should be fragile, clumpy, unresolved. They should resemble shimmering clouds just beginning to remember the idea of shape. Certainly not the massive organized disks and bulges Webb has revealed to us. The contradiction is like listening to a symphony and hearing a grand crescendo in the first few bars. It suggests either our understanding of the tempo is wrong or the symphony is older than we thought. As Nobel laureate Adam Rees once warned, the universe might be trying to tell us something. And perhaps what it is telling us is simple. 13.8 billion years may not be enough time for dark matter to build the universe we observe. When astronomers attempt to reconcile the impossible mass of early galaxies with the known rate of dark matter halo growth, they encounter walls at every turn. Making halos grow faster requires rewriting fundamental physics, as if urging gravity to hurry. But gravity does not hurry. It unfolds like a long breath, slow, patient, deliberate. The early universe cannot simply decide to evolve at twice its natural speed. Not without breaking everything else we know. Some theorists suggest exotic interactions within dark matter. Self-interactions or warm dark matter that moves more quickly. Yet each modification comes with consequences that ripple backward into cosmic, microwave background data, Big Bang nucleosynthesis, and gravitational lensing patterns. The deeper we try to fix the problem with new physics, the more entangled the puzzle becomes. As if the universe resists being patched and instead whispers an older, quieter truth. Perhaps the timeline itself is wrong. If the universe is older, say 20 to 26 billion years, as some modern reinterpretations propose, then the dark matter halos had the time they needed to grow. Under this expanded horizon, those colossal galaxies are no longer premature. They are simply early bloomers in a cosmos with more seasons than we realized. Suddenly, dark matter has the centuries it requires to sculpt vast gravitational bowls, into which baryonic matter can fall and ignite into starlight. The universe becomes less frantic, less forced, more natural. This idea is as gentle as it is radical. It does not break physics. It gives physics room to breathe. In contemplating this possibility, we find ourselves returning to the words of Stephen Hawking, who once said, "To understand the universe, we must be willing to rethink even the oldest assumptions." and the age of the universe is indeed our oldest assumption. The first line in the story: when astronomers describe dark matter forming cosmic structures, they speak of a cosmic web stretching across billions of light years, a lattice of gravity upon which galaxies cling like dew on a spider's thread. This web does not appear instantly. It is woven slowly, delicately, tirelessly. In a younger universe, the threads cannot grow thick enough, strong enough, interconnected enough to explain the architecture we witness at high redshift. But in an older universe, the web gains time to mature, to stretch, to knot itself into grand filaments capable of hosting galaxy clusters the size of entire superstructures. Here, dark matter is not rushed, but patient. A sculptor allowed to finish its work without being asked to defy the limits of its materials. And so the question becomes not why dark matter formed halos so quickly, but why we believed it needed to. For decades, our cosmic timeline has been constrained by the interpretation of redshift, the expansion rate of the universe, and the shimmering echo of the cosmic microwave background. But if even one of those cosmic clocks has been misread, then every age we assign must be reconsidered. An older universe becomes not only mathematically possible, but scientifically compassionate. It relieves dark matter of an impossible burden, allowing it to form galaxies not in a hurried sprint, but in a slow blooming cantus. In this vision, the early universe becomes a long twilight rather than a sudden dawn. Dark matter gathers in silence, a billion years passing like a soft heartbeat. Structures rising from the darkness like mountains emerging through morning fog. Galaxies ignite not out of desperation but inevitability. As cosmologist Joseph Silk beautifully put it, the universe is under no obligation to make sense to us. But sometimes, by allowing ourselves to slow down, to listen, to imagine a longer story, the universe begins to make sense in ways that feel almost tender. And perhaps that is the heart of this meditation. Dark matter, the invisible architect of creation, does not rush. It shapes the cosmos on its own timescale, a scale we may have underestimated. If the universe is older, then the impossible becomes possible. The premature becomes mature, and the cosmic tapestry becomes less tangled. We are left with a universe that feels wiser, calmer, more ancient than our textbooks allow. And in that expanded age, dark matter has all the time in the world to build the structures we now marvel at through the golden eyes of James Webb. So we drift here, suspended between observation and imagination, held by the quiet gravity of unanswered questions. Perhaps the universe is not younger than it appears, but older than we dared to believe. And in that added time, dark matter continues its eternal work, gathering, sculpting, weaving the invisible web that holds all things together. The story of metals in the universe begins long before the word metal meant anything to human minds. In the earliest ages of existence, when the cosmos was still a newborn haze of hydrogen and helium drifting like a silent mist across an endless void, there were no heavy elements to speak of. No iron for worlds to form. No carbon for life to breathe. No oxygen to shape oceans or skies. Just a soft, primordial murmur of the simplest atoms swirling under the gravity of a universe, learning how to become itself. As stars emerged one by one from this delicate fog, they became the first alchemists of existence. Inside them, nuclear furnaces awakened like sleeping fires. Humble hydrogen pressed into helium, helium into carbon, carbon into oxygen. Each step a quiet defiance of the emptiness before them. Every star was a poem of creation, shaping metal out of nothing but pressure and patience. The astrophysicist Carl Sagan once whispered that we are star stuff. And in this ancient beginning, that truth was literal. Yet as we peer today into the high redshift reaches of the universe through the golden eye of James Webb, we find something that troubles the narrative. Galaxies glowing with metal content that seems too rich for their age. Stars whose chemical fingerprints feel mismatched with the clock we built to explain cosmic time. It is as though the universe has lived more years than it admits. As though its early chapters were written in a faster hand than we imagined. The rhythm of metal creation should be slow and steady. First-generation stars live fast and die in brilliant explosions, scattering heavy elements across the newborn cosmos. Second generations gather this material, forming stars with a whisper of metals. Still poor, still ancient. And only after many cycles of birth and death should galaxies shine with the enriched complexity we measure today. This is the conventional timeline, the one taught in textbooks, the one woven from simulations and equations that hum with mathematical beauty. But the universe itself seems unwilling to follow that script. High redshift galaxies, those whose light has traveled more than 13 billion years to reach us, shine with chemical signatures implying generations of stellar evolution that should not have fit into so small a window of cosmic time. They appear too mature, too processed, as if they were ancient spirits wearing the faces of youth. The astrophysicist Priyamvada Natarajan once said, "The early universe may be playing by a different rule book." And as we gaze deeper into that distant light, her words echo like a pulse of truth. If the stars of the early universe forged metals at the pace we believe, the enrichment patterns we observe today should take billions of years to accumulate. Yet we see them in galaxies only a few 100 million years old according to standard cosmological clocks. Something feels out of place, like a melody played before its time. The question becomes inescapable. Did stars simply form faster, burn harder, or die more violently than our models allow? Or is the canvas itself older than we dared imagine? Even more mysterious are the metal-poor stars we observe within our own galaxy's halo, relics from the universe's earliest breaths. Their chemical compositions do not align neatly with the expected output of the first supernovae, as though the astrophysical recipe books of the early cosmos were rewritten by unknown hands. Some stars contain strange ratios of carbon to iron. Others show signatures of enrichment from rare types of primordial explosions. A pattern so inconsistent that many astronomers speak of the early universe not as a uniform place, but as a mosaic of wildly different environments. These variations whisper of secrets that have long been buried in cosmic silence. They suggest that the first stars may not have been solitary giants but complex populations, each shaping metals in unique ways. They hint that the earliest galaxies may have lived through storms of starburst events, waves of creation and destruction more intense than anything we observe today. Or perhaps, as Nobel laureate Adam Rees once remarked, the universe might be trying to tell us that our clock is wrong. If the universe is older than the standard 13.8 billion year model, then the chemical puzzles dissolve like mist in morning light. There would have been time for multiple stellar generations to enrich the interstellar medium, time for heavy elements to rise from the ashes of ancient suns, time for complex chemistry to bloom before our cosmic dawn. The metals we observe at high redshift would no longer be anomalies, but natural products of a longer, deeper, more ancient cosmic story. And yet, we are scientists, and science asks for more than poetry. It asks for mechanisms, models, equations that can stand beneath the weight of observation. Some propose that the first stars may have been far more massive than expected, burning hotter, living shorter, creating metals with unnatural speed. Others suggest that early galaxies were compact cauldrons, their densities high enough to force rapid star formation despite extreme feedback effects. Still others wonder if dark matter itself nudged the furnace of creation toward faster rhythms. But even these possibilities struggle to explain the most perplexing observations. Like stars with metallicities so low, they appear almost untouched by previous generations, yet whose element ratios imply complex histories of enrichment. Or galaxies whose chemical fingerprints show contributions from supernova types that should not yet have existed so early in cosmic time. It is as though the universe is offering us two paths. On one, we cling to our existing timeline, forced to stretch the physics of early star formation into near impossibility. On the other, we accept that cosmic time may be deeper than we believed, that the universe may have lived an entire childhood before the moment we call the Big Bang. When we slow our breath and imagine the cosmic ages drifting past like clouds, it becomes easier to accept that the universe might carry memories older than our equations allow. And in that stillness, in that meditative vastness where thought stretches like starlight, the chemical enrichment history becomes not a puzzle but a quiet confession from the cosmos. A confession that creation has always been patient, always intricate, always willing to take the long way home. The metals of the universe are its oldest stories, written in the language of fire. They are the ashes of dying suns, the fingerprints of supernovae, the shimmering dust that seeded worlds and bodies and dreams. And as we confront the mismatched chemistry of high redshift galaxies and the strange abundance patterns of ancient stars, we may be hearing the universe's soft reminder that it has been telling this story far longer than we thought. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you." And perhaps that is why the earliest metals shine with such quiet defiance. They are the universe's gentle way of guiding us back to humility, inviting us to listen more closely. For in the end, chemical enrichment is not merely a scientific process. It is the universe breathing through time, A long exhale of stars, a slow inhale of matter, a rhythm as old as existence itself. And as we drift with it, floating through the quiet corridors of cosmic history, we sense that the metals we hold so dearly are more than atoms. They are memories, written in the glowing script of creation, waiting for us to understand. The story of our universe often begins with a brilliant flare of creation, a primal ignition we call the Big Bang. Yet when we listen closely to the faint hum of ancient light, when we let the cosmos speak in its own slow language, something softer and older rises beneath the noise. It is the suggestion that the Big Bang was not a beginning, but a doorway. Not the first note, but the moment the orchestra finally became audible. And as we drift through this realization like travelers moving through a cathedral of starlight, we feel time expand around us. Physicist Alan Guth once whispered into the halls of science that inflation was the silent overture before the cosmic symphony began. He said, "The universe didn't begin with the Big Bang, but with a tiny fraction of a second of repulsive gravity." The words felt impossible at first, like trying to imagine the wind before the air. Yet the more we studied the faint patterns etched into the cosmic microwave background, the more we felt those echoes push back against our assumptions. Inflation tells us that before the universe was hot, glowing, and filled with matter, it was cold, empty, and ruled by a strange field that caused space itself to swell faster than light could chase it. In that frozen silence, a patch of reality smaller than a proton began stretching like a slow breath drawn by a sleeping giant. That breath became our universe, but the act of inhaling, the moment before heat, before atoms, before anything we recognize, that is the true beginning we seldom dare to confront. When we accept inflation, we accept that time stretches backward beyond the Big Bang's fire. And with that simple acceptance, the question unfolds like a dark flower in the void. What existed before the universe became bright? What fabric cradled the spark before the spark lit the skies? If inflation is real, then the Big Bang was merely the moment when energy slowed enough to ignite matter and light. It was not the universe waking up, but the universe transforming. The physicist Roger Penrose once mused, "The Big Bang was not a creation event, but a transition from one aeon to another." And as his words drift through our thoughts, we begin to feel the edges of reality soften. Imagine a universe before ours, not filled with stars, but with an ocean of smooth energy, a cosmic winter without form or sound. In that winter, quantum fluctuations stirred like tiny ripples under ice. One ripple grew, then grew again, until the ice cracked and expansion surged outward. That expansion became inflation, and inflation became the scaffold on which the Big Bang would later paint its fire. If this is true, then our universe is not 13.8 billion years old, as we comfortably recite in textbooks. It is older, far older, because inflation itself requires a stretch of existence before the heat we call birth. Perhaps it is 20 billion years old, or 30, Or perhaps the concept of age itself dissolves when we speak of the time before light. As cosmologist Sean Carroll said, "Time is what the universe makes up as it goes along." And if time is woven by the universe, then whatever came before the Big Bang wrote a script we have only begun to decipher. Inflation also suggests something even more wondrous: that our universe may be one bubble among countless others. For if inflation occurred once, why not again? And again? And again? Why would the cosmos stop at creating only one world of galaxies and dreams? In the deep silence before the Big Bang, inflation may have been sewing bubbles of space like pearls into an infinite thread, each bubble expanding, cooling, igniting its own Big Bang. In this vision, our universe is a single bright lantern among an endless lantern forest. If that forest exists, then the pre-Big Bang state was not empty, but overflowing with potential. A ceaseless field giving birth to universes the way stars give birth to light. And here, drifting in the glow of this realization, we begin to feel the humility that great discoveries often demand. The Big Bang was never the whole story, only the chapter we could read with our limited senses. Inflation invites us to flip the page, to see the ink of earlier epochs still shimmering beneath. Astronomer Wendy Friedman once reflected, "We are trying to measure the universe with tools built inside the universe." Her voice feels almost poetic in this context. How could we expect our measurements to capture time before time, heat before heat, the breath before creation? And yet we try, because we are human beings, creatures born from stardust, yet destined to question the darkness that cradled the stars. If the Big Bang was not the beginning, then every age we assign to the cosmos is incomplete. We cannot merely count backward from the glow of the cosmic microwave background, because that glow is only the echo of a moment that happened after inflation. The time before it stretches like a quiet valley shrouded in ancient mist, perhaps unimaginably long. Some researchers argue that inflation may have lasted only a trillionth of a second. Others propose that inflation may have been eternal to the past, a never-ending field rolling endlessly, birthing universes without beginning. If inflation is eternal, then the question "how old is the universe" becomes less meaningful than "how deep is the river of reality flowing beneath our feet?" And as we float gently through this cosmic meditation, we notice how the universe itself feels like a soft breath moving in and out. The Big Bang was the exhale, inflation, the silent inhale before it. And whatever came before that inhale, whatever stirred the field into expansion, whatever whispered the first note into the void, that is the mystery pressing at the edges of our understanding. We do not know what existed before the Big Bang, but inflation teaches us that there was something spacious, something cold, something immense enough to make room for the universe we now call home. And perhaps that is the quiet beauty of this revelation. The idea that the cosmos has a prelude, a memory older than heat, older than stars, older than the clocks we built to measure its heartbeat. The universe did not begin with fire, but with silence. Not with light, but with the possibility of light. Not with something, but with the potential for everything. And in that silence, in that slow breath before the dawn, lies the truth we are only beginning to hear. When we speak of the multiverse, we are really speaking of a kind of cosmic echo, a trembling possibility that reality is wider and older than our imagination has ever dared to stretch. In the quiet space between thoughts, where the universe feels close enough to breathe on our skin, the idea of multiple universes unfolds softly, like a lotus blooming in slow motion. It begins with inflation, the great swelling of space that happened in the first fraction of a second after our own universe was born. And yet, some physicists whispered that inflation may never have fully ended, that in some distant, unreachable expanses it still swells eternally, creating bubble after bubble like cosmic seeds drifting on an endless wind. If this is true, then the universe we call home is just one chamber in a far greater cathedral of existence, a single melody in an infinite symphony. Alan Guth once said that eternal inflation is the ultimate free lunch, a process that keeps creating new universes without ever running out of cosmic breath. And if that breath never stops, then the mother universe, the field in which all bubbles form, might have no beginning at all. Its age might stretch beyond numbers, beyond comprehension, beyond the very structure of time as we understand it. When recent discoveries suggested that our universe may not be 13.8 billion years old, but perhaps something older, twice as old according to some daring models, it is as though the walls of our small cosmic room expanded a bit, revealing a hallway we never knew existed. The thought that our universe could be older fits naturally into the logic of a multiverse, because what is age to a bubble that floats briefly within an eternal sea? What is time to a field that has been inflating forever? If the age of our universe extends backward by billions more years, it does not contradict the multiverse, but rather settles into it gracefully, like a missing stone finely placed into an ancient mosaic. Max Tegmark once said that our universe is not just weird, it is stranger than we can imagine. And perhaps part of that strangeness comes from the possibility that we are not the first bubble, nor the last, nor the largest, nor the most special. We are simply the one that developed conditions gentle enough for stars to form, light to shine, atoms to dance, and consciousness to awaken. If our universe is indeed older than we believed, then our position within the multiverse subtly shifts, like a lantern being carried a few steps deeper into a cavern whose size we cannot see. The universe might imply a recent bubble, a fresh spark in the inflationary sea. But an older universe suggests something different. A bubble that has been drifting longer, shaped by more time, more silence, more cosmic memory. In models of eternal inflation, the distribution of bubble ages depends on how the inflating background evolves. And finding ourselves in an older bubble might be a soft clue, a faint fingerprint of how the parent inflationary field behaves. It raises a quiet question that lingers in the mind like incense smoke curling toward the ceiling of a dark temple. If the universe is older than we thought, then perhaps the transition from inflation to the hot Big Bang in our bubble did not happen when we calculated. Perhaps the glow of the cosmic microwave background carries the memory of a longer prelude. Perhaps ancient galaxies are not anomalies, but citizens of a universe that has known more time than our equations allowed. Leonard Susskind once remarked that the multiverse is not a theory but a prediction of theories that work. And when our timeline begins to stretch and bend beneath new observations, it nudges us gently toward this wider view. Maybe the universe is not simply older, Maybe age itself is not a number but a landscape, different in each bubble. What does it mean for us? Drifting here on a small rock around a small star in a bubble among bubbles. To consider that our universe is older than we thought. It means that the story of being not only begins earlier but also grows larger, richer, more layered. The idea that our universe could be twice as old aligns elegantly with the multiverse, because in a structure so vast, timelines are not uniform. Bubbles can differ in age by billions or trillions of years, and the sea that carries them may have existed forever. In this view, the question, how old, is the universe becomes as fragile and incomplete as asking how old a single drop of rain is within a storm that has no clear beginning. A bubble universe with a doubled timeline simply floats longer in the eternal storm, shaped by currents of inflation, influenced by branching fields, carved by probabilities that stretch beyond imagination. And when we imagine this, we feel a shift inside ourselves, a widening, as if our own consciousness stretches along with the cosmos. We begin to understand that our universe's age is not a limit, but a clue, a faint suggestion that reality has deeper layers, more ancient rhythms, more rooms behind the veil. Perhaps our bubble is older. Perhaps the Mother Universe is eternal. Perhaps both are true in the same mysterious way. A wave and the ocean are both water. And as we listen to these possibilities, we drift slowly through the stars, carried on a soft current of wonder. Understanding that whatever the true age of our universe may be, it is only the beginning of a story far older and far larger than ourselves.